Welcome to this video on fiber optic communication. We'll be looking into mode theory. We'll be discussing on the relationship between rays and modes, why and when to go for mode theory, and the key modal concepts. I am Dr. M. Sumati, Professor of Electronics and Communication Engineering. We know light exhibits wave nature and can be represented using electromagnetic waves. The electromagnetic waves from a light source can be represented using spherical wavefronts as shown in the picture. Wavefronts are nothing but locus of points having the same phase in a wave train. Now, when the wavelength of light is very small compared to the opening or obstacle it encounters, these wavefronts appear as straight lines to the opening or the obstacle, and they can be represented as plane wavefronts. And to each wavefront, a ray can be associated in a direction perpendicular to the wavefront and gives the direction of propagation of the wavefront. Let me summarize. When the wavelength of light is very small compared to the opening or obstacle, it can be represented as plane wavefronts, and rays give the direction of propagation of the wavefront. When can we go for ray theory, or when is the assumption for ray theory valid? It is under small wavelength limit, that is when the ratio of fiber radius to the wavelength is large, that is when the numerator is large and the denominator is very small, or when the wavelength of light is very small compared to the core radius. We have seen in the previous slide, when the wavelength of light is very small compared to the opening or obstacle, rays can be associated with the plane wavefronts. So only when the wavelength of light is small compared to the core radius, rays can be associated with the plane waves, and ray theory is valid. So it is precisely accurate only for zero wavelength limit, but relatively accurate for non-zero wavelength limit, provided number of modes is large. So ray theory is valid for multimode fibers where core radius is large. Whereas for single mode fibers with small core size, ray theory cannot be used. We have to go for modal analysis. What is the advantage of ray optics? It is simple and easy to analyze using ray theory, and it gives the direct physical interpretation of light propagation in a fiber. Let us look at the relationship between rays and modes in an optical fiber. So when light propagates in an optical fiber, electromagnetic waves are present in the transverse direction. That is, if light propagates in the z direction, in the x and y directions, electric and magnetic field standing patterns are produced. Mode is a superimposition of a number of plane waves that collectively form a standing wave pattern in the transverse direction to the direction of propagation of the wave. So mode is a superimposition of a number of plane waves, and we have seen in the previous slide, to plane waves we can associate rays which give the direction of propagation. Therefore, for a particular mode, a set of rays are there which forms a ray congruence, and each ray in this congruence makes the same angle with respect to the fiber axis, and different modes travel along different paths as shown in the picture. And an optical fiber supports only discrete number of guided modes. Therefore, only a discrete number of ray congruences are possible. We have seen, according to ray theory, all the rays that make an angle greater than critical angle at the core cladding interface propagate by total internal reflection. But according to mode theory, not all the rays that make an angle greater than critical angle can propagate. Among those, only those waves which make a particular angle with respect to the axis of the fiber will propagate. How do we determine the particular angle? By considering the interference effect due to the phase of the plane waves, it can be derived. This picture shows the electric field pattern in the transverse direction of propagation of the wave. Since the wave is propagating in the z direction, the electric field in the x direction is shown, the standing wave patterns. Observe, the electric field pattern is different for different orders of the mode. The three lower order modes are shown in this picture. and the order of the mode is equal to the number of zero crossings of the electric field pattern. For TE0 there is 0 crossing, for TE1 there is 1 zero crossing, for TE2 there are 2 zero crossings. And unlike in metallic waveguides where the electric field pattern is 0 at the interface, in an optical fiber which is made of glass which is an insulator, the electric field pattern is not 0 at the core cladding interface. The field varies harmonically inside the core and it is evanescent at the cladding, that is, it decreases exponentially in the cladding. And also lower order modes are tightly concentrated to the center of the core and penetrate less into the cladding, whereas higher order modes the field distribution is more towards the edges. This picture gives the ray in a fiber and the corresponding electric field. The higher or the steeper the angle of the ray congruence, the higher is the order of the mode, and observe, the higher the order of the mode, more energy is in the cladding. Initially, when light is launched into a fiber, many modes exist, but as light propagates, only those modes that are supported by the fiber exist. The rest of the modes cease to exist. What is the need for modal analysis? We have ray analysis, but when should we go, or what is the need for modal analysis? It is required to analyze single mode or few mode fibers. And also when light is launched into the fiber, the field gets distributed among the various modes. So modal analysis is necessary to know the field distribution between the modes. And also when light propagates in a fiber, power coupling between the various modes occurs, and therefore modal analysis is required. Similarly, to analyze diffraction and interference. And also when a fiber is bent, Raytheory says that only certain rays are affected, whereas other rays go unaffected, which is wrong. Mode theory correctly predicts that when a fiber is bent, all the modes in a fiber undergo loss. We will look into the different modes in a fiber. Before that, so that diagram shows an optical fiber. The axis is along the z direction, and that is the direction of propagation of the wave, and x and y are the transverse directions. The electromagnetic field can be described by e power j omega t minus beta z, where omega is the angular frequency and beta is the z component of wave propagation, and it is given by nk, where k is the propagation constant in free space and it is equal to 2 pi by lambda, and minus z in the expression indicates that light propagates in the positive z direction, and beta is an important parameter to analyze the modes of a fiber. So the different modes that are supported in a fiber are guided mode, radiation mode and leaky modes. Guided modes. When the propagation constant beta lies between n1k and n2k, where n1 and n2 are the refractive indices of the core and cladding, then the modes are guided modes. The guided mode propagates entirely through the core. Next, the radiation modes. When light is incident on an optical fiber, those rays that are incident at an angle greater than the acceptance angle get refracted into the cladding, and they are trapped in the cladding. So these form the radiation modes. There is coupling of energy between the core and the cladding modes, and energy loss of the core mode occurs. Going to leaky modes. When the value of beta is less than n2k, the mode or the wave does not cease to exit abruptly. Rather, there is some energy because of the angular momentum barrier in the core cladding interface. So this gives rise to leaky modes. So leaky modes, they propagate to the core but leak out energy into the cladding, and this is by the principle of tunnel effect. So they are like, the leaky modes are like very lossy guided modes rather than radiation modes, and these the boundary between the guided mode and the leaky mode is beta is equal to n2k. So when the value of beta is increased beyond that, the energy in the cladding decreases, and when beta is equal to n1k, all the energy of the wave is in the core. So, some of the parameters of modal concept. First is the normalized frequency or V number. This gives the number of modes supported by a fiber and can be given by the expression V is equal to 2 pi a by lambda into root of n1 square minus n2 square, and we already know numerical aperture is equal to root of n1 square minus n2 square, and substituting that we have V number is equal to 2 pi a by lambda into numerical aperture Na. Observe in the expression, A is the radius of the core and n1 and n2 are the refractive indices of the core at the cladding, and wavelength is represented by lambda. So, when a fiber is manufactured, A, n1 and n2 are all fixed. So, V number depends on the parameter lambda, that is wavelength of light. So, the number of modes supported in a fiber for a fiber that is manufactured depends on the wavelength of light launched into the fiber. Please note the graph on the right hand side of the slide. For the value of V number less than 2.405, only one mode, the fundamental mode He11 exists, and when the V number is greater than 2.405, multiple modes exist. Therefore, for a single mode propagation, V number is less than or equal to 2.405, and for multimode propagation it is greater than 2.405. There is no cutoff frequency for the fundamental mode, and this mode ceases to exist only when the radius of the core becomes 0. For all other modes, there is a cutoff frequency. So, as the value of V number increases, more number of modes are supported in the fiber. And as you can observe, as V number approaches the cutoff frequency, the energy of the particular mode is more on the cladding, and when it is equal to cutoff frequency, all the energy is in the cladding and the mode becomes radiative, and below the cutoff frequency the mode ceases to exist. So, the number of modes supported by a step index fiber is given by the expression m is equal to V square by 2, and for large values of V, the ratio of power in the cladding to the total power is given by 4 by 3 root m. Next, we will be looking into linearly polarized mode, which is an important consideration while analyzing the modes in a fiber. So, solving Maxwell's equation and applying boundary conditions, the modes of a fiber can be analyzed. For a metallic waveguide, the Maxwell's equation give rise to TE, TM and TEM, that is transverse electromagnetic waves, but TEM waves are hardly found in optical fibers. The TE and TM waves correspond to the meridional rays travelling in the core of the fiber, and the suffix L and M indicated by two integers is given because an optical fiber, which is a cylindrical waveguide, is bound in two axes. In addition to the TE and TM waves, because of the core cladding boundary condition and coupling of the electric and magnetic fields, hybrid modes exist due to the skew rays, where both Ez and Hz, that is the electric and magnetic fields in the z direction of propagation, are also non-zero, and these hybrid modes are represented by EH and HE. EH means the electric field is dominant and HE means the magnetic field is dominant. Modal analysis for an optical fiber is much complicated compared to that of a metallic waveguide. Therefore, weakly guiding fiber approximation is made use of over here to simplify the modal analysis. What is weakly guiding fiber approximation? That is for very small difference between N1 and N2. So, in practical fibers, the difference between the refractive index of the core and the cladding is very small. N1 minus N2 or delta is very small, and therefore, the light that is launched into the fiber, sufficient amount of it travels through the cladding also. That is, the guiding nature of the fiber is very weak. That is called weakly guiding fiber approximation. Under these conditions, the electric magnetic fields can be considered to be transverse and they are linearly polarized. So, irrespective of the fields, whether they are TE, TM, HE or EH, they degenerate into linearly polarized components. So the mode pairs with identical propagation constant but different patterns form the degenerate modes. So these degenerate modes, a group of the degenerate modes, they degenerate into a particular linearly polarized modes. So a linearly polarized mode is made up of a number of degenerate modes. To summarize, a superposition of the degenerate modes that have similar propagation constant correspond to a particular linearly polarized mode. So in practical fiber, the light propagates as a linearly polarized mode and not as TE, TEM or HE modes. The relationship or the group of degenerate modes that form a linearly polarized mode is given for LP0N, LP1M and LPVM. So this represents the various linear polarized modes and the degenerate modes that form the given linearly polarized modes. This picture, the subdivision A indicates the 3 lower order linearly polarized modes and B gives the exact modes that form each of these linearly polarized modes. And subdivision C gives the electric field distribution representation of these exact modes, and subdivision D the intensity distribution of the linearly polarized mode. Now looking into two important parameters for single mode fibers. The first is mode field diameter or the effective diameter. This gives a measure of the width of distribution of electric field intensity. It is alternatively equivalent to twice the spot size. Unlike in a multimode fiber where numerical aperture and core radius is used to specify various parameters, the electric field distribution is used to predict fiber properties in a single mode fiber, the properties such as waveguide dispersion, bending loss, etc. So for a single mode fiber, M is small and the fraction of power in the cladding is large, and the graph shows for a Gaussian distribution, the mode field diameter, which is equal to 2 W naught, can be given as E naught by E square, where E naught is the maximum intensity of light. So the single mode fiber mode field diameter is greater than the core diameter. The next important parameter is the propagation mode. So single mode fiber has only one mode of propagation, LP01, which is made of two degenerate modes which have similar propagation constants, but their plane of polarization is orthogonal. So we have two orthogonal planes that propagate in the fiber. For an ideal fiber with perfect rotational symmetry, both the modes propagate in the fiber with the same velocity. Therefore, their polarization state remains unchanged. Whereas practical fibers have imperfections such as non-circular core, lateral stress bending and so on. So these cause the refractive index along the x and the y direction to be different. Therefore, the orthogonal modes, the two degenerate modes, propagate with different velocities, and therefore there is a phase difference between the two and the state of polarization changes. So this difference between the effective refractive indices is called fiber birefringence, that is two refractive indices, which is given by Bf is equal to Ny minus Nx, and also the propagation constant, which is equal to Nk, is given by K naught into Ny minus Nx because of the existence of two refractive indices. So as the degenerate modes propagate along the fiber, because of different refractive indices along the two axes, the velocities of the two modes is different, and therefore the phase difference exists, and therefore the state of polarization changes. So as the mode propagates along the fiber, the polarization state keeps changing, and it is noted that after a certain distance, the phase difference becomes an integral multiple of 2 pi and the original state of polarization is restored. So this distance over which the beating occurs is called the fiber beat length, and it is given by Lb is equal to 2 pi by beta, where beta is the propagation constant. looking into some important parameters for graded index fiber. In a graded index fiber, we know the refractive index in the core gradually decreases as we move outward radially from the center of the fiber, and it is constant at the cladding. So the refractive index n of r at any point can be given as n1 into 1 minus 2 delta into r by a the whole power alpha the whole to the power half for r between 0 and a, that is for the core of the fiber. And for r greater than or equal to a, that is for the cladding of the fiber, refractive index n of r is constant, that is equal to n2. Here r is the radial distance of the fiber and alpha gives the shape of the refractive index profile, and the graph shows the shapes for different values of alpha. When alpha is equal to infinity, it is a step index fiber as indicated by the solid black line, and for alpha is equal to 1, that is a triangular profile indicated by the blue dotted line, and alpha is equal to 2 gives the parabolic profile shown by the solid red line. Dispersion is minimum for alpha is equal to 2 in a graded index fiber, and it is a popularly used. The numerical aperture at a point r for a graded index fiber is given by Na of r is equal to Na of 0 into square root of 1 minus r by a the whole per alpha at the core, and it is 0 at the cladding. And the number of modes in a graded index fiber is m is alpha by alpha plus 2 into v square by 2, where alpha is the refractive index profile and alpha is equal to 2. The parabolic refractive index profile is the most commonly used profile, and for that value we get m is equal to v square by 4. We have seen that for a step index fiber, the number of modes that is supported by the fiber is v square by 2. So for a graded index fiber with parabolic profile, it is v square by 4. So the number of modes supported by a parabolic profile graded index fiber is half that supported by a step index fiber. So in this video, we have seen the relationship between rays and modes, and when and why to go for mode theory, and some of the key concepts of mode theory, and some important parameters for single mode fibers and the parameters for graded index fibers. These are the references used. Thank you.